Hello, and welcome to the first video on a new topic, which is stereochemistry. We've seen a number of forms of isomerism. We've seen geometric around a double bond. We've seen positional and structural. We've seen functional group isomerism. This is a new type, and it happens only under a particular set of circumstances. That is, you have to have an sp3 carbon, a tetrahedron, and you have to have four different substituents for different things around that carbon. Now, those four different things can be like a hexane and an octane, and you'd think, how different are they? Well, they're different. So it only has to be in some way different. And when you do, what you call this carbon in the middle is a chiral carbon. Now, this was first discovered or discussed maybe 150 years ago, and it's played a role in a lot of chemical understanding. So the bottom line is, without going into history too much, is that when you have four substituents, there is a problem, if you will, in that this is not the only way I can put four substituents around this. I could switch any two, the blue and the white. I could switch red and blue. I could switch any two. And if I switched any two, what I'd end up with is one version like this. I'll hold the blue in the back. And I could end up with another version like this. Again, I'm holding the blue in back. What you have, basically, I'll hold the greens on the outside, is two molecules that are looking at each other in a mirror. See how they're looking at each other in a mirror? Whatever one is, the other is the opposite in the mirror. And we actually call these non-superimposable mirror images. And why non-superimposable? Well, a famous and, of course, logical example are your hands. Your hands are mirror images of each other, right? And so one hand is looking at the other hand in the mirror, and little fingers coming out towards you. And yet they're non-superimposable, meaning I can't get them to be the same. I can't put my left glove on my right hand, not easily, and not logically. So these are famous non-superimposable mirror images, right? I can look at my nose as the plane of the mirror, if you will. And so these are called stereoisomers. Stereos, back in my day, if you will, were very big, a speaker in that corner and a speaker in that corner, and some sound out of that and some sound out of that. And they provided a duality. And so here we have stereoisomers. And when you have two stereoisomers, we call that a chiral carbon. And we have a special word for each one of these stereoisomers. They're called enantiomers. So here's an enantiomer. Here's another. They're looking at each other in the mirror. The whites are coming towards you. The reds and blues are back. The greens are down. They're in my hands. So we can describe these stereoisomers and enantiomers in a number of ways. So I'm going to start writing while I talk. Let's look at some chiral carbons and therefore molecules with two stereoisomers. And you should have an ability to draw like this. And since this is a carbon chemistry course, while it is true that other atoms can have chiral centers, we're only going to discuss carbon because, well, that's what you came here for. So I'm going to put three things around that carbon, and then I'm going to make a mirror image to the extent that my artwork allows me to do so. And there is the mirror where they're looking at each other in the mirror. Those are two enantiomers around a chiral carbon, two stereoisomers. I could write these, I could do a number of other examples. That carbon that you see with a star next to it is chiral. Why do we know that? We know there's a hydrogen. And so that's a methyl and an ethyl and an OH and an H. And those are different. So that carbon is chiral. We'll often see it denoted by hashes and wedges. So let's have the OH come at you and the H going back. So there's a chiral carbon. And I could have switched the OH and the H, and I'd have the other enantiomer. I could also draw these any number of other ways. A famous way to do it, kind of a version of skeletal structure, is to take the four substituents on that 2-butan-2-ol and put them randomly around that one carbon, that starred carbon, that chiral carbon. We'll return to this. This is called a Fisher projection. I could, of course, draw these as Newman projections. Easily enough, I could draw a chiral center. All you need to know is that four different things are around that central atom. And that front carbon there is chiral. Note that the back one is not chiral. Why? Because there are particular rules. One rule is sp3, the other is four different substituents. And if something has two hydrogens, the back carbon has two hydrogens, then it's not chiral, right? As long as you have four different things, it is chiral. So for instance, all the amino acids have this form. We'll just say R. Carboxylic acid and amine. That chiral carbon is, only chiral if that R isn't an amine, a carboxylic acid, or an H. In fact, glycine, one of the 20 naturally occurring amino acids, is an H for that R, and so is the one non-chiral, or what we call achiral molecule of the 20 amino acids. So other things to know about these chiral carbons that will play a role in a later date, and that is, if it is chiral, here's a plane, a mirror, if you will, but a plane of symmetry. And I'm going to put a carbon in there with an H in the plane and a OH in the plane. Now, if there is a plane of symmetry, meaning the stuff on, so the C and the H and the OH are in the plane, the methyl on the left and the methyl on the right indicate that that's a plane of symmetry. If it has that, then it's not chiral. Symmetry. So another way to look at the same idea. Now, it's very important to know what we're talking about here. And one of the things that, bedevils organic chemists is that enantiomers have identical physical properties, which kind of makes sense. They're the same molecule with just a stereo center different. So as you can imagine, let's say you make, doing some chemistry, you make both of these enantiomers when you do a reaction. How do you separate them? They boil at the same place. they have the same density, they have all the same characteristics, they have the same charge if they have a charge. So they are very hard to separate, but their chemical properties can be dramatically different. We can have one stereoisomer smell like strawberry and the other stereoisomer smell like caraway seeds. Almost everyone at this point brings up the case of thalidomide. Thalidomide was a drug that helped women in the 60s with morning sickness. And one stereoisomer was beautiful. It totally helped with morning sickness. It was totally harmless. It was great for pregnant women, but they were hard to get apart. So they just said, well, if 50 milligrams of one enantiomer is good for them, let's just give them both, not separate the two forms, well, we'll talk about that. The one stereoisomer and the other one, the two enantiomers, we'll give them 100 milligrams of an equal mix. And the other 50 mgs will just be nothing. And it turned out they weren't nothing. They caused massive birth defects. So an amazing, interesting story in sort of health and biology. I was saying that amino acids are chiral. They have a chiral center. And it should be noted that only one of the two enantiomers exists in biology. The other one's meaningless. And so too for DNA. DNA has a sugar and it has a base attached. We'll make C. That is terrible. Where did my head go? So you could see right there that carbon number 1 famously, has 4 different things on it, so it's chiral. And only one of the two chiral forms, one of the two enantiomers, exists in nature. And it's actually that version that you always see. I'll show you one more way of looking at them, especially when you're looking at cyclical chiral molecules. Let's put a BR on there and let's have the cis version of that. Well, we can draw it edge on. And what you do is you draw it like this. And you make this edge darker because it's coming towards you. And you indicated cis by having them on the same side of the plane. And these are called, oh, how do you spell it? And you'll see these as well on occasion. So there's the cis, and of course, you could also equally draw the trans form of this. So there are a lot of ways to write these as you go. So let's talk about a little bit of the mathematics, only a little, but it's worth noting. And that is one of the things that makes these interesting is that they have handedness. They are one enantiomer or the other. One of the ramifications, if you will, is that if you were to take light and you were to put a polarimeter, meaning a slit, let's say a vertical slit, so that only light coming straight at you now, was coming into a molecule, into a cuvette, incident to a material. And if it was coming in and you had a chiral carbon, it would deflect. So instead of being going out still vertical, up and down, if you will. So instead of coming in, let's say the light I'm showing edge on a sine wave of light. Instead of being up and down, one version of this would deflect the plane polarized light in one direction, and the other enantiomer would deflect it in the other direction. These are called, for logical reasons, a polarimeter. And you can tell which version you have. And we actually know how much certain molecules deflect. They will have numerical values, but only numerical values for one enantiomer purely. So we have enantiomeric purity. And so when we do a reaction, we get two stereoisomers, maybe we don't produce pure enantiomeric purity. Maybe we get a 50-50 mix. And if you do, well, let's say this deflects minus 35, and this deflects positive 35. By the way, we have names for these, which I'll get to. The one that deflects left is called S or D. In biology, they call it D for dextro. The S, actually, I love this. It's sinister, because left is sinister after all. And the other one that we'll use is right, but you hear in biology, levo. R or levo, S or dextro. Or, sorry, S or L, and R or D. Dextro is right, dexterous, as opposed to sinister. But if you get an equal mixture of right and left, well, they cancel out. Now, all of a sudden, you don't have the light deflecting. It's effectively achiral again. We call this a racemic mix. And that's a useful term. If you hear racemic mix, you know that they got equal amounts of both stereoisomer, which is unfortunately very common in true synthetic chemistry. I've been there. But sometimes you get mostly R or mostly S. You get it deflected mostly in one direction. So let's say that pure, I have an example, pure cholesterol will deflect some amount. We tend to use this term, this alpha of dextro is minus 31.5. But it only deflects 27.4 according to the practice problem I drew up for myself. Well, you can describe the amount of the value from the polarimeter and the known established value. So let's say you got 27.4. Let's say it's in the negative direction, which is R. And it's actually 31.5. You could say, because I did this math, that it was 87%. You multiply it by 100 R, right? And so we have a term for that. And enantiomeric excess, or percent enantiomeric excess, is something that organic chemists are always discussing, bragging about. And what it basically means, be aware of this. What it basically means is that 87% of it is R. So fully 13% is a racemic mixture of RS. So when I say 87%, I'm actually meaning that R is, divide that in half, then 90, what is 3.5%, and S was 6.5%, right? Because 13% was racemic, canceled each other out, and 87% was pure R, enantiomeric excess. And I want you to know those terms because it's pretty common. Let's say that you have analyze a cocaine sample, and the cocaine, I'm using this example because it's in the PowerPoint, is 68% enantiomeric excess S. Well, what does that mean? What it implies is that 32% is RS equally, because they canceled out and the rest was S. So in fact, you get this number 68%, you're like, well, that's rubbish. But it's actually 84% S and whatever, 16% R. And so people brag about, I got 92% enantiomeric excess. That's actually 96% R, right, and 4% S. Anyway, an important number to know. So let's start fresh and talk about R and S. So as we said, R means that it's going in a clockwise direction or it's going to the right, and S means that it's going in an anti-clockwise, counterclockwise direction to the left. So let's make up a real example and talk about how you designate a molecule as R or S. So there's a couple of rules. One, you're going to try to get the lowest molecular weight back. And with examples, these will make sense. And then designate by molecular weight. If there's a tie, keep going until the tie is broken. I'll show you what I mean. Oh, and it's always worth noting that a double bond is like being attached to two C's. You can consider that to be attached to two C's. A triple bond would be like being attached to three C's. And this is for tie-breaking circumstances. So let's do the simplest example. Let's make a carbon, and we'll put the H back. There it is behind the plane of the board here, or the plane of the camera you're looking at, screen. And we'll put in front a methyl and an OH and I don't know, an ethyl. So what you're trying to do now is designate what is the highest molecular weight. Oh, well, oxygen's obviously one. And then I have a carbon, but I also have a carbon. But this carbon is attached to three hydrogens. And this carbon is attached to two hydrogens and a carbon. So it wins the tie. So it's two, and this one is three. In other words, what you're looking at is the priorities going 1, 2, 3 in a counterclockwise way. So this molecule would be S, well, we'll write 2-butanol, or butan-2-ol, but it's the S version, right? So we'll do a couple of more examples. Let's do this one. Let's just randomly assign things, Cl, CH3, and OH. I put the OH up again. So we've got the first thing, right? We've got the H back. We'll have to talk about what you do on the next screen with an H that's not behind the plane of the board. Well, chlorine is higher in molecular weight than the other two. Oxygen is second, carbon is third. So this goes this way. So that's R. And that's really all there is to designations. So let's say you have and you're trying to determine whether this is R or S. And you're thinking to yourself, but I've got a problem. H is in front. Well, here's what I would say to do. If you swap any two atoms, any two of these balls, if I swap them, I make the other enantiomer. So here's what I'll do. I'll swap the hydrogen for the thing in back. I'm going to swap these. That's going to go back there, and that's going to go up there. And I'm going to make the wrong enantiomer, and then I'll know what this one's called, if you see what I mean. So I'm going to make BrC, CH3. I'll swap the H for the OH. And now I have 1, 2, 3. And that's counterclockwise. But I've just told you about the other enantiomer. So that guy is R. Simples, right? And you can do single swaps with any atoms that you want. Let's look at this another way. We did this earlier. This will be pretty common. There's 2-butanol, but is it R or S? Well, 1, 2, 3. The H is back. That's R. What else? Here's one. So what are we talking about here? Well, one is easy. You'll notice that the lowest priority in this case is a C with 3 H's on it. So I've got the right atom back. If I didn't have the methyl back, I could swap it. Now here's a carbon that's attached to 1 carbon and 2 hydrogens. And here's a carbon attached to 2 carbons. So this is clearly the second priority, and this is the third. So like that, it is S. So you can do any number of these. Let's say you had so do the single swap. I'm going to say you do the single swap. Whoops, that's rubbish. H is now back. 1, 2, 3. That is S. So that is R, 2-bromobutane. And that's how you designate R and S. I'll leave you with an example that's actually nicked off a video. So let's see. So the question is, are these two enantiomers or are they the same molecule? Well, we can name it. One of the functional groups I didn't ask you to name is a CN attached to a carbon, which is called nitrile. So this is 3 carbons, 2 fluoro, nitrile. Right, so this molecule is this. I don't know why I drew it so close. So are they the same molecule or are they 2 different stereoisomers? C, N. Well, all we have to do is name each one. Well, in the case of the one on the left, oh, I've got to do a single swap. I'm going to change the H back there and the CH3 up here. Now I have 1. Fluorine's bigger than carbon. Carbon's attached to a nitrogen. 3. So that is S. But because it's a single swap, you have to be careful and remember you single swap. So that's R. This one, oh, the H is back. So 1, 2, 3. So that is S. These are enantiomers. All right. I think that's enough right there for a first video. We're going to get more engaged in these stereoisomeric properties in a video right below this one, stereochemistry 2, if you will. And all of this is from chapter 5. So easy enough to find. So thanks for your time.